Awesome, thank you. Let's talk before lunch. So hi everybody, my name is German Parisi, and thank you for a nice introduction. So I wanted to talk about some of my work at McD Tech Labs for McDonald's Corporation that we are developing right now in Mountain View. And also some work about, lifelong conversational AI. So what's the underlying technology that we are using and other people are using in the scientific community, and the potential for real world applications. So perhaps a bit of overlap with previous conversations in terms of advances and recent advances in natural language processing. We have a lot of interesting applications in automatic speech recognition, so the ability to transcribe text from raw speech signals, reaching human level performance for some of the tasks. And as well as machine translation, so ability to translate from any language to any other target language. So examples of that are Google Translate and so on. Of course, the quality of those translations vary according to the complexity of the text and the target language, but anyway, there's been a lot of progress. And from then going to natural language understanding on LLU, in which we're not only transcribing text, but we also have higher level reasoning over the text, right? And there are a lot of examples for giving commands to robots, so they have to understand something that we say and they will perform specific activities. And then go into conversational assistance. So in that case, those are agents that do not only understand what we say, but can also respond, so they can answer using human language. So we can have text-to-text applications like chatbots, or more complex ones that actually are speech-to-speech. We have also examples from Amazon using Alexa or Apple using Siri. And if you use those, that kind of technology, you know that is very interesting, very promising, but of course there's a lot of room for improvement. So before we go further, just brief overview about the underlying technology that's being used by a number of these applications. So if we just think about the past or recent past and the present of NLP. So we started, a lot of the applications that I mentioned are using specific recurring neural network architecture, which is called LSTM, so long short-term memory, that is able to process sequences, right? Because actually speech or language, it's of course it's in the temporal domain, so it requires the processing of sequences. And one of the most, let's say the most popular applications, the most popular architectures for processing text were in this case the bidirectional LSTMs that were able to process like states from the past and from future events. So in that case, they enrich the representation of sequence processing by using bidirectional layers. And the CTC, or connectionist temporal classification, which is addressing more the problem of sequences that maybe contain repetitions or vary in terms of the timing. And more recent architecture, which is the GRU, which is basically conceptually the same concept of the LSTM, but has a fewer number of parameters, so that makes it more efficient to train. But in terms of performance, empirical studies show that LSTM and GRU are more or less on the same level for a number of tasks. And then there's a more recent stream of research, which is transformers. I think it was mentioned on one of the previous talks, in which here, if we think about LSTMs, they do pretty well in word by word. And if we think of like short sentences, like sentences maybe that go from a dozen words to 100 words, whereas actually transformers have a much richer representation of the context. So they can go for sentences from hundreds of words to actually entire Wikipedia articles. And that's what makes them very interesting for a lot of applications in the real world. Some examples are the bidirectional encoder by Google AI, in which they have very interesting results on a series of NLP tasks. And Ernie 2.0, which actually is a very recent architecture that actually is able to keep learning from different data sets. So one of the issues that we have when we train this kind of neural networks is that we need a defined batch, so a training set, and then we deploy that architecture, right? It's out there, but it's really hard to integrate novel information into that architecture. And a even more recent architecture, which is Reformer, which is kind of a very efficient version of Transformer. And it's very interesting because of the way, conceptually, it's very similar to Transformer. Because of the efficient way that it's trained, we can actually process articles up to 1 million words. And that's what makes it very promising for a number of applications. Now, as you said, all these architectures are great for processing text, for processing raw speech signals with different limitations. But one of the key limitations here is that we collect a lot of information, we have large data sets, and once we train our neural networks, it's really hard to integrate novel information to them. This problem is called actually lifelong learning or continual learning, which is the ability of a neural network to integrate novel information without forgetting previously learned tasks. So from a more technical perspective, all the connectionist architectures, so not only recurrent neural networks, but also convolutional neural networks and so on, suffer from the so-called catastrophic forgetting. That means that as soon as I start training the network with a novel task, I may forget previously learned tasks. So this is prevented in most of the architectures just by having a batch of training samples and just showing these samples again and again to the network. So multiple iterations. But that sometimes is not possible, or if I have a really large batch of training samples, that's not really the best thing to do. So retraining from scratch those models whenever I have novel information available is also not the way to go. So if we think instead about the brain, which is so far the best learning machine we have, we can talk about the plasticity, stability, balance, or what's the dilemma to find the right level of plasticity and stability. That means that I have to have a neural architecture which is plastic enough or flexible enough to learn normal architecture, but also stable enough not to forget previously learned samples. And in the scientific community, people have been working on that, so finding a right balance of stability and plasticity, having some layers with pre-trained networks, and then only fine-tuning the uppermost layers to learn novel tasks, which works to some extent or not. And importantly, something which is crucial when I have a lot of data and I want to train our models is having transfer learning. That means how quicker can I learn a future task if I have learned a subset of tasks in the past, and vice versa, how much I can improve the performance on previous tasks when I learn something new. And this problem is it's been ongoing, it's been there for a while. Since the 80s, actually, people have been working on how to mitigate the catastrophic forgetting in neural architectures. And most of the time, all the approaches that people have been using for that are motivated by neuroscience. So what's happening in the brain, because the brain has a number of mechanisms actually to prevent catastrophic forgetting, right? We, as humans, or also high animals, they learn over a lifespan without really this catastrophic forgetting. We do forget stuff, we do forget a lot of things over time, but that forgetting is not catastrophic unless we have specific brain injuries. So recently this topic gained a lot of interest in the scientific community. So after some workshops and meetings we have at NeurIPS and ICML, we decided to contribute to the community with a review paper in which we describe all different neural mechanisms that are used to prevent catastrophic forgetting and in neural networks, which have a lot of potential actually in real world applications, right? If you think about systems that can collect a lot of information, and again, we think about Siri or Alexa, sometimes they collect so much information and that information cannot be integrated into the systems, right? So they have different training mechanisms, but it's really hard for their systems to really integrate that knowledge on the fly or actually generalize properly from all these huge amount of data that they have. So back to McD Tech Labs. Last year, October 2018, McDonald's acquired a startup who was working on neuroscience-inspired technology for NLP, and we established a new R&D lab in Mountain View, California. So this lab will be investigating and advancing the state-of-the-art in voice-based technology and apply that technology to a set of applications from McDonald's, which is mobile apps, kiosks, which so far are, they have haptic feedback, but would be great to actually be able to interact with these kiosks using natural language, and the drive-through, which I will talk about later. So the idea of applying state-of-the-art technologies to improve the overall customer experience, so how customers can interact with a different number of applications in a more natural way, and also to improve the experience of the crew members at the restaurants, right? To make their job easier so they can focus on more elaborated tasks. So the main focus is drive-through, right? If we think about McDonald's, we have over 14K stores in the US only, and about 90% of them have a drive-through. And the drive-through is a very challenging, it represents a lot of challenging conditions for this kind of technology, right? Because first of all, we are outdoors. We don't have, like in the case of Siri, a microphone and a cell phone. So we have a mic in the drive-through. Customers arrive. They may have different accents. They may come from different parts of the US. Many McDonald's actually are on highways, so we get people from all over the country. So we have to account for all those challenges and apply state-of-the-art technology for actually understanding and taking their order faster and in a more accurate way. Because this human-to-human interaction is good, but it's not perfect. Sometimes there are mistakes in the orders. And as I said before, this would give customers and employees a better experience. Of course, customers will get their order faster and more precise, and then employees won't have to be listening to the orders of people, but they can be actually in the kitchen preparing food faster. And as I said before, this represents a lot of challenges because we have to be very robust and, to a set of environmental challenges, or people can formulate or phrase requests in very different ways, right? Just for asking for a burger, they can say a huge number of things, and the solution has to be scalable. That means that if we think about all the information that we have to process, and for example, every McDonald's has at least 2 lanes, so our system is currently running real time. So we've been testing this solution in around 6 restaurants, mostly in the Chicago area, and we will be scaling to a huge number of restaurants the next year. So it happens that you're around some McDonald's and you may go for a drive-through, you may be able to test this new technology, which is very interesting and challenging, and I think this is a really nice use case for applying this kind of technology. Now, the problem continual or lifelong learning is so interesting, and there is so much interest in the research community that at the time we actually created a nonprofit research organization that started with with only 10 people, and we just wanted to share our interest for continual learning and connect different researchers. And we also created our own collaborative research lab, in which we actually investigate a number of core research questions, like first of all, what are the key principles that actually govern continual learning in the brain, and how actually we can leverage current models, learning models, to be flexible, robust, and scalable, just like the brain is. And we are currently collaborating with a number of people from other companies that actually express that interest in continual AI, such as Google AI, DeepMind, and Facebook. And also Mila, who is, I don't know, for those of you who know the Montreal Institute of Artificial Intelligence, Benjo right now is offering a new course on continual AI, which is also a great platform to bring people together and keep advancing the research field. All right, so I would like to thank you very much. I will just keep it brief, and if you have any questions, just let me know.